Tu non c'hai?
Io ce l'ho, non se lo metto a palla.
Perché?
Vedi che il mio cellulare come funziona bene.
Perché tu non vedi niente.
No, aspetta, vado qua.
1, 2, 3.
Wow.
Testing. 1, 2, 3.
Ok.
Ok, è una risa di lei.
A huge delay. Wow. Okay, so thank you for your patience. And so the goal of the session today will be to perform some simple calculations on some small molecules so that hopefully you will get an understanding of what you can do and what kind of information you can get with computational chemistry. We will be using two different softwares. One is Gaussian, which is a commercial program, actually. This actually you will use an old version of the program. It's Gaussian 09, from which I have the license. And then we will use a second program, which is Gauss View, which is associated to Gaussian. It's basically used to prepare the calculations that we are going to run and visualize the results. So that's what we will do. So we will start by modeling a very small system, and we will just try to do some small effects. So basically, well, I'm sharing the screen, so doesn't make sense to, like this. So basically, we are starting by preparing a geometry of ammonia that can make sense, let's say, as a starting point, and we will optimize it using different computational methods and look a little bit at the nitrogen-hydrogen distances and the angles of that molecule and see how accurately we can reproduce those structural data with different models. Okay. So if you all open Gauss View, you see the screen, right? I think you should have like a white page or a blue page that is empty. Okay. So now we need to prepare like a starting model for our molecule. If this is ammonia, you see what so try to follow me, right? So you see here that you have like an icon 6C, okay? If you click there, you go to the periodic table, and there you can select a nitrogen to start with, right? And we want an sp3 nitrogen. So down here we click on an sp3 nitrogen, and then we click on the screen, right? Be careful not to click a second time. And now you can rotate by holding the left button of your mouse and moving the mouse, right? You can rotate it. Could you all do it? Yeah, okay. So you see that we have like a reasonable starting point for an ammonia molecule, right? Then if you have here an icon with a question mark, you see here on the top. If you go to the question mark and you click two atoms, you should get the distance down here, right? So that's 1 angstrom as a starting point, okay? And we can have also the, sorry, I lost my mouse. Okay, you can also measure the angle, and this should be close to 109, right? As we expect for sp3 nitrogen. So now we will run the optimization, right? We will start with a simple method, for instance, a semi-empirical method, right? If you remember, basically using electronic structure theory, you have, well, 3 families of methods: semi-empirical methods that use some parametrization to simplify calculations, ab initio methods, and also the density functional theory methods, right? So we will start with AM1. AM stands for Austin Model 1, right? So that was a a semi-empirical method that was developed in Austin, Texas. So to do so, we will prepare the input file for our calculation. For that, we can use directly Gauss view. We go to calculate, you see that on the top. And the first option we have there is Gaussian calculation setup, right? So there we have already, a new screen so that we can prepare our calculation. So first we need to select the job type here. You see that we have different options. One of them is optimization, correct? And another one is optimization plus frequency. We will run that one, okay? Optimization plus frequency. I will explain now why we will run the two calculations one after the other. And we will optimize to a minimum, okay? This is what we want. And then we have to select the method. You see there. We will model a ground state. And here, instead of Hartree-Fock, which is the default method here, we select semi-empirical. And we select AM1, okay? So we are almost ready now. You see that here below, we have the charge of the molecule. In our case, it's 0. That's a neutral molecule, and we have the spin, okay? So that's important information we always need to provide to the system, because while the program will count the electrons that you have in your molecule, right? And the count comes from the atoms that you have, right? But we also need the charge, right? So that we have the overall number of electrons for our system, and also the spin multiplicity. This is obviously a singlet because there are no unpaired electrons. Handling systems with unpaired electrons is a bit more tricky, okay? But well, it's not anyway too difficult. Good. So in principle, we are ready to start. So we will run the optimization. If you remember from the previous session, an optimization generally goes through first derivatives of the wave function with respect to the nuclear positions, all right? So that if we want to reach a minimum, the first derivatives should be 0, right? So this is what the program is using to try to find the minimum energy structure, right? Or at least a local minimum. And then we should always check calculating second derivatives, so frequencies, that all frequencies are positive, and that means that we are indeed in a local minimum on our potential energy surface, okay? So clicking submit, we get a message that tells us that we need to save our input file. We can save it anywhere. I'm working in the desktop, doesn't matter. So I will save this file as AM1NH3, for instance, so that I recognize what is there. Save. And then we get this question, submit the following file to Gaussian, and we simply answer yes. And now the program should run. That screen, so Gauss View is connecting directly to Gaussian and launches the program, and the program is running. It's giving us some information over there. But at the end, we can go through the output file if we want, and analyze what kind of information we have there. So it's now doing first derivatives. Well, first doing the self-consistent field calculation, so that we get the coefficients that express the molecular orbitals, and then doing first derivatives and trying to find that, you see there, trying to find the nuclear positions that corresponds to 0 values of the first derivative, okay? And once that's done, we requested a frequency calculation, so we requested second derivatives as well. Is the program running for all of you? Yes? Okay, that's good. So once the calculation finishes, it gives a kind of message. And so that indicates that the calculation finished successfully. Do you want to close the Gaussian window? We can answer yes. And I think we should have in the same directory, hopefully, a file with an extension log. Let me see if I find it. Do I need to minimize everything? Well, maybe close this. And maybe it's faster like this. Yes, so in the same directory, you see that I have a file with an extension log that contains my results from this calculation. So you can open the log file. You can open the log file with Gauss view. And now you will have here the optimized geometry, okay? It was simple, right? So now with the question mark, you can measure the distance, for instance. And now you see that it's not exactly 1 angstrom as in the starting geometry, but almost. So the bond distance is, maybe you can write down here the values. So at AM1 is 0.99, whatever, 998. And the angle, so this is the distance. And the angle should be somewhere close to 109 as well, right? 109.09. Okay, you should all have around these values. Yes? Good. Now this is the optimized geometry, but I mentioned that we need to check always if we actually ended up on a local energy minimum or somewhere else on the potential energy surface. So for that, you can go to the results menu and you go to vibrations. You got it? And there you go. You have vibrational data here. You see, you have a list of vibrations, correct? And you have all vibrations positive, correct? So that means that your optimized structure is actually a local energy minimum on the potential energy surface, okay? It's not a transition state or is not, any other point on the potential energy surface. So always after running an optimization, you need to really confirm that you got an energy minimum and not anything else. You can ask questions, of course, and interrupt at any point. Huh? Good. We can also analyze a little bit the frequency data. You see here? For instance, let's select this one here. So the one with the highest frequency, or actually wave number. That's the wave number, right? In reciprocal centimeters. And we can play an animation so that we can see the nuclear movements that corresponds to this vibrational frequency. You saw it? What is it? Symmetrical stretching vibration, right? And that comes at 534, right? So the symmetric stretching vibration, maybe it should. Okay. So how was it? 3534. In reciprocal centimeters. And then you have two vibrations with the same wave number you see here, which is the asymmetrical stretching vibration, right? And they are degenerate. That's why they have the very same energy. So that if the point group of the molecule is C3V, right? For ammonia. So these are E stretching vibrations, right? So these double degenerate. Okay, so this is 3, 4, 6, 4. Just to compare with the experiment. That's the asymmetrical vibration. And then it should come bending, right? Which is this one. You can also rotate the molecule while. And here we also have two degenerate bending modes, right? 1764. And that's the bending vibration of the H and H angle. Okay, and finally we have here this final vibration, which corresponds to the inversion of the ammonia molecule, right? So the nitrogen is like passing from one side of the plane defined by the 3 hydrogen atoms to the other one. Okay. Good. So, and this is 113 or 1140. And this is actually, I don't know how this vibration is called. Anyway, it's an inversion, right? Of the ammonia molecule. Okay, so one thing we could do is just compare this with the experiment, right? So the experimental data in the gas phase is over there. So the bond distance is 1.017 angstroms, so that's in picometers, correct? And the angle is 107.8 degrees. Okay. So well, we see that there is some deviation, but not very much. And you have also the vibrational frequencies. So the experimental is 3414. So we are a bit off. So we calculate a little, the energy a little bit too high. 3336, 1627 versus 1764, and finally 950, and that's 1140. Okay. Not very different. And anyway, this is just a semi-empirical method. So it's among the simplest methods that we can use within electronic structure theory. Okay. And still, anyway, well, it's quite common that the vibrational frequencies are overestimated. The energy of vibrational frequencies are overestimated. They can also be corrected, just multiplying the wave numbers by an empirical factor, depending on the method, something like 0.97 or 98 or something like that. And that will bring our vibrational frequencies closer to the experiment. Okay. So this is a very simple example, right? So among the list that we have there, we can try now a calculation using Hartree-Fock, for instance, and a small basis set like STO3G. So for that, we go to Gauss view again. We can start with the log file. So we stop the vibrational movement, the animation, and we can start from this geometry to run the optimization with a different model. Okay. So again, we repeat the process. We set up the calculation. Now the job type will be optimization plus frequency again. And now in method, instead of semi-empirical, we select Hartree-Fock. And then the basis set, we will start with the minimal basis set, which is this STO3G. STO stands for Slater type of orbital, and 3G approximated with 3 Gaussian functions. That's the minimal basis set that we can use. Okay. So I think the calculation will be very fast. We save again. So I will save this, for instance, as Hartree-Fock STO3G and then NH3, so that looking at the name, I can understand what I am doing, right, with the calculation. I save, I submit, and if everything goes well, Gaussian is launched and it will start running. It is running, actually, okay? So Hartree-Fock would be ab initio already, although the simplest ab initio method that we can use, so that actually we are taking electron correlation, if you remember, in a kind of average way. So like each electron is like reacting to an average of the electron density of the all remaining electrons. Okay, so there it goes. Probably your laptops are faster than mine, which is quite old. Maybe you finished before me, right? Okay. But it shouldn't take too much time. So now, another detail is that if you know, with this calculation, with this Hartree-Fock calculation, we selected the method, Hartree-Fock, and the basis set, right? You remember the three approximations that we need to make, right? It was the Bohr-Oppenheimer approximation, the method, so the Slater determinant and the number of them and so on, and the basis set, so the functions that we use to describe the orbitals. Before, with this semi-empirical method, actually we don't select a basis set because it's already defined together with the method, right? Now, with Hartree-Fock, no, this has finished, okay. We can, we must select actually a basis set. Okay, so we can open the log file again, okay. And I just wanted to run a calculation with an electronic structure method, the simplest one, right? So it's Hartree-Fock and a small basis set, just to compare the results with a more, let's say, sophisticated method. So here the distance is 1.032, right? So it has increased a lot, or well, significantly, I would say. And so maybe I should write down distance here. 1.032. And the angle probably has worsened a lot. 104.16. So it has worsened a lot, particularly compared with the experiment that was 107, I think, right? So, and for the, well, we didn't check that all frequencies were positive, but they should. And you see here that also vibrational frequencies are not very good, right? So we go to 4,100, okay? And the vibrational modes should be identical in principle. But now that is a difference here, right? So the asymmetrical vibration now comes to with the highest energy. And it should be actually like this, right? The asymmetrical vibration always comes with a higher energy than the symmetrical one. But the wave numbers are quite off with respect to the experiment, correct? Okay, so this was just to illustrate how a semi-empirical method can provide results that are comparable or better than calculations using electronic structure theory if we are using a small basis set and also with the limitations of Hartree-Fock. So now the next step is to run a calculation with a better model. So for instance, here we can use B3 LEAP and this basis set, okay? So B3LIP is one of the DFT methods. It's probably the most popular density functional, so that it is used, you know, sometimes by default, right, to run calculations. So again, we can repeat the process. Gaussian calculation setup, and then the job type should be still optimization plus frequency. Run state, here we select DFT, and the default functional is B3LIP already. And then as a basis set, we will select this 6311G basis set, which is already quite good basis set. So it's triple set basis set. So it uses like 3 functions to describe, for instance, the valence orbitals of each atom, right? So for nitrogen, we would use 3 different functions to describe the 2s and 2p orbitals, right? So this is already a quite good basis set that we can like improve using some polarization functions like this D or this P polarization function. So this will add D functions to nitrogen, okay? Although in principle, we don't need to include D functions, okay? And this will also include P functions for hydrogen, even when we don't need neither, right? But just to, yeah, that improves the performance of the basis set, and it allows like the orbitals to change shape a little bit. That's why they are called polarization functions. And we can even add here diffuse functions. So if we add here 1+ is just for nitrogen would be, and 2+ would include diffusion functions also for hydrogen. So let's put 1+, and hopefully this will come out in a reasonable time. Huh? So I will launch it. First, I need to save. So I changed the name to, sorry, B3LIP and 6311G DP. And that's enough, I think. Save. And hopefully we can complete this in a reasonable time. So you will probably finish earlier than me. You see that the program is using symmetry to perform the calculation. If you see some of the information that is passing, you see some symmetry labels over there, some A's and E's, right? So it's using symmetry actually to simplify the calculations a little bit. Yeah?
It's finished. It can be because of my C.
It can be. It can be. Just open the log file and play with it. So just open, for instance, visualize the frequencies. If you have all frequencies positive. Yeah, I don't know what I can do actually. No, then it is not completed. Something went wrong. Maybe we can just try to have a look. But this is the input file. The output file is the extension is log. Is this one? Okay. It is the one that you so then you hidden in the Gaussian calculation setup. Okay. Job type. And which one?
Because in the calculation, job type was energy and motion.
Okay, but yours is right. You try again, yeah. Hopefully it's not because memory is wrong. You have to save. Save. All right, that's correct. Yes. Yes. Now, there's maybe one problem with memory or something like that. I think so, because that's another question. The problem is not actually. But maybe it's not doing something. Link diet. So I think it's just a problem. So maybe you can run the calculation again with a smaller base. So like, for instance, yeah, instead of 6, remove that. Maybe keep the polarization and then as well. And then here you select 6 pre-bunching. Maybe that will make it small enough, hopefully. And try again, and hopefully it will work. Okay, so mine finished. No? Same better. So that's great. I don't know. I would need like, to analyze it for a while to see why this error is coming. Okay, so let's have a look to the results. So I should close, open the log file. And here we go. Here we go. So what is the distance now? It's 1.015. So 1.015. I think this is very close to the experiment, right? How much was in the experiment? So it was 1.017. Yeah, that's very, very good, right? And then for the angle, we got 107.95. And experiment was 107.8. Wonderful, right? Yes. Okay, so this was a little bit to, yes, understand that we have to be careful with both the method and the basis set, right? The two things are important. So using a more sophisticated method, but a small basis set may deliver worse results than a simpler method with a better basis set, right? Of course, we will always, depending on our system, we need to find the balance between accuracy and computational time, right? Always, we should aim at using the highest or the most accurate method within or taking into account the limitations of our computational resources, okay? Obviously, with the laptop, those limitations are huge. If you are interested in starting doing computational chemistry, then you will need to have access to a supercomputing facility, right? So that you can connect and send your calculations and so on. All right, so the aim would be always to find the best method that we can afford. Good, so it looks like with this last calculation, we have a nice geometry, right? I didn't check the frequencies, but probably they are a little bit off always, so overestimated. Was it this one? So results, vibrations, but they are certainly much better than with Hartree-Fock and the small basis set, right? So, okay, you can just compare them more carefully if you want, but still, as I mentioned before, we can always scale the calculations if we are really interested in vibrational frequencies, because we need to assign our infrared spectrum or our Raman spectrum, right? Computational calculations can help on that. So the next step that I would like to make now is to try to calculate the transition state, right? That's interesting because if we can calculate transition states, in principle, we can study reactivity, right? Because we have the energy of the transition state and the ground state. We have the activation energy barrier, and in principle, we can calculate rate constants and so on, okay? So we will model a very simple system, which is again ammonia. And in particular, we will study the inversion of ammonia, okay? And well, make sure that you keep this very last calculation, because we will need to compare our energies for the ground state and the transition state, all right? Okay, so to look for the transition state, we have to first think a little bit, right? To have an understanding of what we are looking for. If with the nitrogen atom is going to flip from one side of the plane defined by the 3 nitrogen atoms to the other, it should pass through that plane. And therefore, most likely, the transition state responsible for that process should be planar, right? So let's generate a trigonal planar structure of ammonia, okay? So we go to nitrogen, and then, yeah, maybe like this, I'm not sure. Or maybe just a nitrogen atom, sorry. Let's see if it works. And we add 3 nitrogens, and it's already planar, okay. Do I repeat it? So, where is it? Nitrogen. You select a nitrogen atom, click, and then with this tool here, which add hydrogens, okay, we click 1, 2, 3, and we have something trigonal planar, right? Otherwise, we could manipulate also the angles and the dihedral angles, but this is a very easy way to get something trigonal planar. You are there? Great. So now let's run the calculation again. So same procedure. Calculate, Gaussian calculator setup. Job type, optimization plus frequency. Now we are going to try to locate the transition state. So it will be critical to calculate the frequencies, right? It will be critical. Otherwise, we cannot confirm that we have a transition state. Okay, we will go to the ground state anyway, to the electronic ground state for that particular geometry. We will use DFT, we will use V3lib, and we will use the same basis set that we used before. And this was 1+, and I think this was DMP, right? Very good. And I launch quickly because I'm slow compared to you. So I think I will call it with the very same name as before, but adding before TS, which then identifies to me a transition state. Let me see if no, I think like this I'm going to optimize. Sorry, I was too quick. I think it was in job type. Okay, yes, I forgot this. Okay, we optimize a transition state. And then actually we need to calculate the force constant somehow. And we can use it at every point. So what is it? Force constants, calculate at all points. This will be tough, even for a small molecule, okay? So with this, we are telling the program to calculate second derivatives for each step of the optimization, right? So hopefully it will end up with the geometry of the transition state characterized by a single negative vibrational frequency. Okay. So you got it? Yep. Okay. Submit. Let me check the, I don't know if this is correct. Yes. Okay. I think it is. Save. Yeah. Yeah. And hopefully I have enough memory. Yeah, it looks like it's running. So it's very important also to perform our calculations, our separate calculations, using the very same procedure if we need to compare, information from two different calculations, right? So we need to optimize and characterize the transition state with the very same method that we use to characterize the ground state. Otherwise, the energies are not comparable, okay? So that's also very important, not to mix up different models or different basis sets, for instance, then you get strange results. Oh, it was really quick. It was so fast that I doubt maybe I made some mistake or forgot something. Let's see. Is it trigonal planar? Well, it is. You got it like that as well? Good. So the first thing now is go to vibrations and confirm that we have one and only one negative frequency. Is that the case? Yeah. Very good. So that means that we are in a transition state, but we still are not sure that this is the right transition state. Okay, it could be some other transition state on the potential energy surface. Of course, this is a simple molecule, so there aren't many options. But if you have, a larger system, you may end up calculating a transition or optimizing a transition state that corresponds to a process that is not the one you are really looking for. Okay, so we always have to play our vibration, so the animation of our negative vibrational frequency, so that we see how nuclei are moving for that negative vibrational mode, and the atom displacements should correspond to a movement that connects reagent and product. If so, we are pretty sure that we got the transition state that we are looking for. And indeed, in this case, it looks like that negative vibrational frequency corresponds to the inversion of ammonia, right? Any question? No? Oh, sure.
Going to decide which of these methods use because we have reference. But in case we have polymer or more complicated molecules, how do you choose the right method?
Okay, so the first part of the answer would be check the literature. So just read a little bit and see what kind of methods people is using and which of those methods provides the best results, and that will give you something to start with. And then once you have selected the method, you can consider other issues like, well, the basis set, of course, that's important to use the largest basis set that you can afford. And then some maybe additional things, like if you are modeling molecular systems in solution, maybe you can try to incorporate some solvation model, or you may ask yourself if you have to incorporate relativistic effects and so on, right? But to start with, I think reading is important. Okay, so Now we calculated the transition state so that we can, in principle, estimate the energy barrier for the inversion process, right? So one possibility is go through the output file. Actually, I will open an output file just so that you can see it. It's not that you even need to do it right now, but it's just it is hard to reach my desktop. Maybe through here. Yeah. So I can open this one. For instance, this is just a text file. So I generally open them with WordPad. And there you have, well, a lot of information, actually. You are generally interested in a part of the output file. So things about the copyright, the authors of the program. I think, I don't know if probably in this version is not still Cosi, right? But in the newer versions, he is. And then information about your input, so these instructions that you give to the program, and then geometrical information here. So these are coordinates for your molecule. And then you are going to estimate the first derivative of these variables, which are actually distances and angles. That's very often molecules the structure is defined instead of Cartesian coordinates in the so-called Z matrix. That is a list of distances, angles, and dihedral angles, so that you can also define your structure. And then this grad indicates that you are about to optimize, and then more information on structure, distance matrix, so that's geometries. Here is information about the basis set. So we are using a standard basis set that is here. And then the number of basis functions that we are using 40 basis functions that include 16 primitive Gaussians. So the number of Gaussian functions. So that also gives you an idea of the size of your basis set, right? So in general, for, let's say, if you are using a supercomputer, you can go rather easily to, I don't know, 2000 Gaussian functions if you want to optimize, all right? So that's like a reference for using at least DFT, of course, right? Other methods are, more expensive. So information about the orbitals and the symmetry of the orbitals, right? This comes from this initial guess that is written there. So the program has some function to run a simple calculation and obtain an initial guess of these coefficients that are multiplying the atomic orbitals, actually, right? And then the self-consistent field procedure is that is used to solve in an iterative way this problem, so that we calculate an energy that is given there. You see this minus 56.58. This is the energy of the system in Hartrees for the initial geometry, okay? And then more or less this section is repeated over time for each optimization step, okay? Well, you have also dipolar moments and, well, some other information over there. And then you have information about the convergence of your optimization process in terms of the force and the displacement of the atom. So once these thresholds are achieved, the program understands that the optimization has converged, okay? And so on. So it's not that important that we go through the whole output file, but Gauss view actually what it's doing is just extracting the information from the output file, right? The information you are interested in. So to calculate the energy barrier, we need the energy of the ground state and the energy of the transition state. So this can be easily done Why I don't have access to the summary because this is the input file, not the output file. Okay. So, okay, I start with the transition state. If I go to results summary, there is a window here, small window, where you have some information. Among this information is the electronic energy here in Hartrees. But besides that, since we did second derivatives, the program, using some statistical mechanics calculations, can estimate also the enthalpy and the entropy for the system, so that we can even calculate Gibbs free energies. All right. So we have all this information here. We have the electronic energy in Hartrees. We have, well, of course, the 0-point energy correction. So you know that your vibrational energy is not zero even at 0 Kelvin, right? So you always have a 0-point energy correction that you need to take into account. And since you calculate the frequencies, you can incorporate that correction to the energy. And then you have these thermal corrections to energy in enthalpy and free energy, so that here by the end, you can have this electronic energy plus thermal free energy correction, which incorporates the 0-point energy as well. Okay. So this is the value that actually we need if we want to calculate the activation Gibbs free energy, all right, with our method. So maybe I should write down, this is, can you tell me the energy? Minus 56.56. Right, and this is for the transition state. So now we need this, the same value, but for the ground state. Results summary thermal, and is this minus 56, 56, 6. 56, 6. 439, okay? All right, and this is for the ground state. Okay, this is in Hartrees. So now we can make the difference among the two. Do you have a calculator, or can you do the difference? So it would be, you can just forget about the 56, right? So it's, you see that by the way that the energy for the ground state is more negative, slightly more negative than the energy for the transition state. And this is what you actually expect, right? So you should do 0.566439 minus 0.560734. And you get a tiny number, but that's because you get it in Hartrees, which is the atomic unit for energy. You got it? You got it?
0.005705.
Okay, don't delete that number. Now you need to multiply that number by, let me see, I'm trusting my memory. I think it is 627.5045, if my memory is not failing at this point. Okay. And that brings you your energy difference to kilocalories per mole.
So it's just a conversion.
It's just a conversion factor that I did so many times that I remember. And then please multiply by, because I don't know the conversion factor to kilojoules per mole directly. So now please multiply that by 4.18, right? You got the number? How much is it?
14.9640.
Okay, that's enough. So the activation free energy is 14.9, is it?
Yeah.
Okay, kilojoules per mole. well, many computational chemists work in kilocalories per mole. So if you read papers, generally energies are given in kilocalories per mole, even when it is not the international system unit, right? Okay, I try to use kilojoules, but still, yeah. Anyway, the conversion is straightforward, so. I think in the next slide, I have the experimental energy barrier. It's 24. So we are a bit far, huh? But this is expected. This is expected because actually Mithril works very well for some, or actually for many chemical problems, but not so well for others. And I mentioned in the previous session, right, that this is one of the limitations of DFT, or one of the problems, because there is no universal density functional that provides good results for every problem, right? So there are actually functionals that were developed to provide accurate energy barriers. Okay, for instance, some of the programs, some of the functionals of the Minnesota family that start with an M, for instance, M06 and things like that. These were parameterized in a way, because then most of density functionals are parameterized in a way, because you need to describe the electron density somehow. And that parameterization, in some cases, incorporates data sets with energy barriers, all right? So I'm not very surprised that, okay, the performance is not really very good, but yeah, we could improve it for sure, selecting a more modern and better functional for this purpose. Actually, I think in Gaussian 09, these Minnesota functionals were not even implemented, if I think so. So we would need to use a newer version of the program. Okay, how do you see it? You have questions? No? Okay, so I have other exercises that we can do. We could, for instance, study the potential energy surface of ethane, all right? And we can use, again, B3LEAP and the very same, well, maybe without the diffuse function, it will be a bit faster, okay? So I'm just closing all the ammonia windows. Okay, and now let's start with a new window. And we select tetrahedral carbon here. Okay, so we have methane. And if we click again on a hydrogen, we already have ethane in an alternate conformation, you see, right? So this should be a reasonable model to start with. So we will again start by optimizing and running the frequency so that we get the optimized geometry. Should be quick, I think. So let's use optimization plus frequency, DFT B3LEAP, and maybe the very same basis set as before, I would say. I think we can afford it. So DP, and I think I can submit it. I think I didn't forget about anything. So C2H6 B3LEAP, and some information about the basis set. And that should be enough. Okay. So I have launched the calculation. We will start them, studying a little bit the potential energy surface. Is it working for you? Yeah. And in your case, you had problems before. Is working? All right. Okay, great. Okay, so mine is a bit slow. Have you finished? Yes? All right. Let's see how far I am. If I can see if I'm approaching the threshold for convergence. Now it's optimization completed, second derivatives, that's it. Yeah, it's starting now the frequency. So this is actually your output file, like the one I opened before with WordPad, and that is just like going through the screen. Yeah, it's almost there. Okay, I got it finally. So, oops. So now I open the log file and I just check that I got the optimized geometry, that I'm in a local minimum, right? So where I am here. You already did? Okay, you all got all positive vibrations, yes? Very good. So that makes us ready for the next step, which is exploring the potential energy surface. So let's see if I can do it in the first attempt. Okay, so actually I leave everything, no, just, sorry, optimization only. We will not run frequency over the potential energy surface because we will have negative values. So we know we are not in a local minimum. So just optimization. We leave the very same method. And then, do I do it from here? Maybe, Okay, so then I will submit, but not submit. Save. I will save it with the very same name that I had, but now I will add before PES, so potential energy surface, right? So that I know, but I will not submit it to Gaussian. Is that is easier, instead of giving instructions with Gauss view, opening here the file and modifying here. Should be called PES something. Where is it? Maybe it's at the end. Yes. So I got it here, right? We actually didn't look at the input file. Huh? So it's actually very simple. Well, we are not indicating a title. We could, of course. So the first line actually is that percentage sign and then CHK gives the number of a file with an extension CHK that stores a lot of information during the calculation. Okay. And actually it's in your computer, but it's not an ASCII file. So if you need to retrieve like additional information from this file, you need to transform it before. So there are ways to do it. But in general, it's not a file that you will need, right? Then the second line is the command line. So Gaussian is working with keywords. So the first keyword is OPT, that tells the program performance optimization, okay? And this is what Gauss view, when we set up the calculation, is doing for us, right? So preparing this input file. And the second option that we have there is B3lib, so the method, the DFT, the density function that we selected. Then slash the basis set, you see that is there. And then geom equal connectivities that, apart from the Cartesian coordinates here, we have the connectivity among the different atoms, which in principle we don't need, right? So with these electronic structure methods, we are working actually with nuclei and electrons. So we don't assume anything a priori concerning if atoms are bonded or not, okay? Of course, in an indirect way, we do, because we start from a geometry that is reasonable from the chemical point of view, but the calculation does not need any assumption on that, okay? And then, well, you see also that over on the top of the Cartesian coordinates, you have a 0, which is the charge, and 1, that is the spin multiplicity, okay? So this is how the input file looks like. So I'm just going to modify slightly this input file, writing OPT equal mod redundant, if I remember well. And then I will delete geometry equals connectivity so that I can delete also the section here on the bottom, which is not needed. And then I have, I think in the presentation, the instruction, just so that I don't, maybe I have to check this. But anyway, so we should paste here this instruction, doesn't matter. But I'm not completely sure about the numbering, okay, of the atoms. So I have to come back here, and let's say I want to explore, let's say this angle, okay? This angle is roughly -60, you see, right? This is what we expect. And the atoms are 2158. So I'm going back to 2158. I need to remember this. 2158, okay. And so this instruction here tells the program that we have, well, those 4 atoms. 4 atoms define a dihedral angle, right? If we gave 3 atoms, we would be exploring an angle, or 2 a distance, okay? So we will explore the dihedral angle defined by those 4 atoms. The starting angle is 60. I think we can delete it. So it will use just the angle of the optimized geometry. S, it indicates scan. So the program will scan that coordinate. And then we will do 13 steps, changing 10 degrees each step, okay? So that means that we will cover roughly, since the first optimization will be with the starting geometry, we will cover 120 degrees. And this is what we get, what we want, right? So we will move from one alternate conformation, going through the eclipse conformation, to the alternate conformation on the other side. Okay, so if I didn't make any mistake, I can close this. I think should be okay. So now I open with Gauss view. It can be done also directly from Gauss view, but it's just that I'm more used to work with the, with input file itself. So, okay, we go anyway to calculation Gaussian. And now, this is strange. Yeah, it is correct, I think. I think it is correct. Let's see. Submit. Yes. It is running. I think it is going. Yes, very good. So, well, doing calculations, you do many mistakes. Every day you forget about some detail, and then you, of course, realize, and you go back. I mean, that's, or at least this is how it works for me. So what we are going to do, or we are doing right now, is actually for each of those 13 steps, we are relaxing all the coordinates of our molecule except that dihedral angle that we are selecting, okay? So except that dihedral that is constrained by the instruction that we have given to the program, all the rest of the coordinates that describe our molecule will be relaxed. So this is what we call the relaxed potential energy surface scan, okay? And this is very useful when we study reactivity and we want to locate transition states, right? Before for ammonia, it was straightforward to understand, that the transition state should be trigonal planar and to generate a structure. But quite often it's not that simple to find a good input structure for the transition state. So in that case, it may be very useful to run, a relaxed potential energy surface scan, and then you go to your energy profile, you take the geometry that corresponds to the maximum in that energy profile, and you afterwards try to optimize the transition state, okay? So we need to perform like 13 optimizations. That will take a while for me. You already done? Not really, huh? Okay. That's, yeah. The molecule is also a bit larger than ammonia, and you know that this is not scaling linearly with size, right? So yeah, it takes probably a while. Good, and with after this example, we will try to model something, let's say more, yeah, a larger molecule, like a small complex we will model. So I don't know how far I am. Tell me if any of you have finished. Yes? You have finished, Daniela? Okay. Because if it takes too long, then we just decrease the size of the basis set or something, right? So this, yeah, the purpose here is not to have very accurate results, so just that you get a feeling of what you can do. Sorry again. You can read a PDB file with Gauss view and generate your input structure from there. You can also open a zip file or mol or mol2 files. So Gauss view reads like most of structured files. Yes. Generally, when you publish computational results, you need to add, at least in the supporting information, all the coordinates of the geometries that you calculate. Yeah, PDB is a database, right? Actually, I think there are some databases, but not really for structures. I think there are databases, for instance, for potential energy surfaces calculated with very much precision. But no, I think there are no databases. So you need to go through the individual papers and just copy the coordinates and then see. So that is the most interesting part. So it's where actually the information is, right? Did any of you finish? No, okay, so this is taking a while. So maybe I was too optimistic with the basis set. Actually, I think I can already open I hope I don't spoil the calculation because it's changing. Not sure. If I copy the file to another place, I think I can do it. So that I can see how many points I have. So if I copy this, let's say, and I take it to another directory, like this, where I just store some of my calculations, then I should be able to open the file without spoiling the calculation, hopefully. Okay, calculations, here it is. Will I be able to open? So it gives me some message because the calculation is not complete, so that's normal. Well, I have 7 points already. So should finish, yeah, relatively short time. You see my scan? But I still only have like 1, 2, 3.5, 6, 7, yeah, half of the points, right? And it might be that this very last one is not really still completely optimized. That's why it's a little bit off, right? But here it should be, around here should be the transition state, because that would correspond to an eclipsed conformation, right? You see? You see it below? So this should be about the structure of the transition state. So you can move like this, you see? So we have is a plot of energy in Hartrees versus the angle. So that we are scanning. So I think in my computer, I'm about at the half of the calculation. So probably some of you will finish relatively soon. So, yeah, everything good. Okay. Hopefully. So if everything goes good, yes. Well, when you finish the calculation, you can open the scan and see your energy profile, right? Yes, but this is not finished. Again, I didn't hear. Actually, you can run half of it in this case because of symmetry consideration, yes. But yeah, if you had, for instance, chlorine on one of the carbons, then it would not be symmetrical, of course. Yeah. Yeah, but that's right, yes. So let's see if, how far we are. So you did not finish yet, any of you, right? Let's see. So I copy the file again. I move it here. Oh, no, it's not this file, actually. Sorry. So let's see how many points more I have. Copy, replace. I think I need to close the old one. Come on. So many windows here. Okay, so I'm opening again just to track how far we are from convergence of all of the steps, of course. So 11. So yeah, I still missed 2 points. So I guess some of you have finished or not. Right. So you have the whole energy profile. I know what this. Okay. So results scan. So in my case, it is starting to look good, right? I still miss a couple of points there. But yeah, So in the eclipse conformation, I am on the highest energy, as you see, right? Okay. And then, yeah. Yeah, I still miss 2 points, but I already can actually calculate the transition state starting from the geometry and the energy barrier as we did for ammonia, right? Okay. So I think it doesn't matter if I finish those 2 steps or not. So you see what relaxed potential energy surfaces can look like and why it is useful, particularly if you study reactivity. Okay, very good. So we can move to one more problem. And this will be, I would like to model cis and trans plating, okay? Which are relatively small metal complexes. I would say real life metal complexes, right? So it's not like just simply a curiosity, but they are molecules that have some, yeah, important application. So let's try to model the 2 isomers of that complex, so both the cis and the trans isomers. And then we will have a look at the vibrational frequencies. We will have a look at the structure also, if we see, for instance, some trans effect or things like that. The relative energy. So let's see which of the isomers is the thermodynamic isomer. And yeah. So we did again to prepare like starting geometry to initiate our calculations. So we click on the periodic table as we did before, and we select platinum. You have it here. You have many options here. So we go straight to the square planar platinum, right? So this is what we expect. So it draws a platinum with 4 hydrogens, and now you have to select, let's start with the cis isomer, for instance, or maybe half of you with the cis isomer and half of you with the trans. So I think that would make sense, right? So let's say this side trans and this side cis. So you trans and you cis. It doesn't matter if it is the other way around. Okay, so now we select chloride, and I will model, for instance, the cis isomer. So if I click with the chlorine on the top of the hydrogen, I introduce these 2 chloride ligands, and then I need to add like ammonia. So I will add the nitrogen atom in each of the other 2 positions, and then with this function that allows you adding hydrogens, you click 1, 2, 3 times, and you end up with a reasonable structure to start with. Yeah, and for the trans isomer is the same. Okay. Well, here we have more atoms, so I anticipate that the optimization may be a little bit more tricky. Usually when I run this exercise, some of you end up having some negative frequencies because, for instance, the rotation of the ammonia and things like that. But it is interesting to see anyway. So hopefully some of you will end up with the minimum energy structure, and maybe some other with a transition state we were not looking for, but still in that way we see the importance also of running frequency calculations. Okay, so now calculate Gaussian calculation setup. So job type, let's go for optimization plus frequency. We will optimize to a minimum, and we will use the FT. And we will use B3-lip, yeah, why not? I mean, we could select another one, but even if it is in the list here, maybe it is not incorporated in Gaussian also, because I think Gauss view is more modern. This version is more modern than the Gaussian version. So let's stay with B3-lip, even where we could find more, yes, accurate options. And now this is important point. because here we have a heavy atom, right? Remember that I mentioned that if we have heavy atoms, relativistic effects are important. Generally for geometry optimization, yeah, it's enough to just select a basis set that incorporates an effective core potential to describe the inner electrons. So you know that the inner electrons are moving much faster than the outer electrons, right? Because they are more strongly attracted by the nucleus, right? So they have to move very fast, and they approach the speed of light, or a significant fraction of the speed of light, right? So with these effective core potentials, we have some pseudo potentials that describe the inner electrons, and then some basis set that describes the valence electrons. And that's most of the time enough for geometry optimizations, right? So there are different pseudo potentials, but if we select, for instance, lang L2DZ, this one here, this basis set already incorporates an ECP for heavy atoms, an ECP that was developed in Los Alamos. That's why the reason for the name is this is Los Alamos, and then it's the double set valence basis set together with this effective core potential, right? In Los Alamos, they have like a very strong research center on nuclear chemistry, so that they are interested in heavy atoms, right? So they also have theoreticians, among them those that develop this as ECP. So selecting this specific basis set, we are already selecting a pseudo potential for the inner electrons of platinum, the associated basis set for valence electrons of platinum, and also a double Z basis set for the light atoms, right? Everything in one step. It may be if you are like going deeper in computational chemistry that you have to like select these parts by yourself to optimize your model, right? We're also reading some literature. Okay, so charge is 0. That's fine in this case, but we also need to pay attention to the charge. If there is no combination of, if that charge does not match with the number of electrons of your system, then you will receive an error message. And that happens when your charge is off by 1 unit, right? But if it is off by 2 units, the program will calculate. And you will get results, right? But they will be corresponding to a completely different system, right? Okay, so it's important to pay attention to this, and well, the spin multiplicity if you have unpaired electrons. Okay, so I will just launch the calculation. So this will be B3 lib lang L2DZ and cis plat. Okay, because I'm still running the previous one, the potential energy surface. Actually, it finished. Okay. I think I have to start again. But probably everything is ready. I think so. Okay. So it's calculating. Probably you started before me and you are faster, right? So I should save the talking for later while the calculation is running. Okay, so the process is as usual. And yeah, as soon as some of you finish, just let me know so that, well, you can open the log file and check the frequencies. That's the first thing to make sure that you have energy minimum. So this is a square planar. Just thinking that another thing that we could do is to look at the molecular orbital. That's something that we didn't do. So if this is, since it is a square planar molecule, then the LUMO should be like a dx squared minus y squared orbital, right? And the HOMO should be like the dz squared or the dxy orbitals, it depends. So, okay, let's first optimize and then we can try to look at the orbitals, which is also, well, interesting to see. So let me see if I can understand how far I am. I think what will take a little while is the frequency calculation afterwards, because now the number of atoms has increased significantly. But I think my optimization is still ongoing. Yeah, I'm still a bit far. What about you? You can see on the screen when it passes, you know, the convergence criteria, how many yes you have. I still have 4 no's. So that means I'm still far. So you see 4 no's there. So yeah. So you need 4 yes to complete the optimization and then the frequency calculation. Okay. Yeah. No, it's not a problem.
It's correct.
It's correct.
Okay.
So just check that you have all migrations positive. So that's also interesting. They are all positive, yes. So that you are in the energy variable.
Okay.
So the problem that she had is that the ammonia ligands were not drawn with bonds to platinum. Okay. But that's just because Gauss view understands that that distance is longer than a regular platinum ammonia bond. But that's it, you know. From the perspective of our computational method, as I mentioned before, we are not making any assumption regarding if atoms are bonded or not, right? We simply start with some reasonable geometry according to our chemical understanding, and that's it. Okay, so there is no parametrization or anything. So the fact that you can call that a bond or not is conventional, right? Because we call a bond a distance of within a given range, right? But it's simply conventional, so that's not a problem at all. You can draw them, of course. Okay. There's a tool there, so you like, yeah. But it's just a matter of representing the molecule. So you had I forgot. You had the cis or the trans. Cis. You have a trans ready? Yeah. Yes, very good. So one thing we can do is to look a little bit at some of the vibrational modes and how we can use them, for instance, for structure elucidation. So actually what you have there is the far infrared. Okay, so my calculation finished. Yes, okay. So what you have there is the far infrared spectrum of those two compounds. So basically, this is the trans and that's the cis, right? And according to the symmetry of the two molecules, you can already anticipate that some of the metal ligand vibrations may be split in the cis isomer because of the lower symmetry. The symmetry would be C2V, right? And is it? Yeah, C2V, yes. And for the trans isomer, we have D2H symmetry, if I'm not mistaken. Okay. So due to the higher symmetry, some of the vibrational modes may be degenerate and non-degenerate for the cis isomer. Okay. So that can be used actually comparing the experimental and calculated spectrum to identify, for instance, the complex that we have prepared in the laboratory, right? And you can imagine that we know we have a complex with that, let's say, composition, because we have the mass spectrum, we have maybe another analytical data, but we are not sure about the isomer that we have. So maybe looking at the metal ligand vibrational bands, we can assign the structure and understand the isomer that we have, right? So if I go here, open the output file. Okay, what is it? Now I start having too many. Here it is. Okay, so you see what I mentioned before. So there is no line drawn, but still that's a bond, right? So that's 2.1. 2.1 angstroms is a typical platinum nitrogen bond. So yeah, maybe I'm not sure if the experimental distance could be maybe 0.02 angstroms shorter or something like that, but not much shorter, all right? So results frequencies of vibrations, and then we can identify the metal ligand vibrational modes. So here we have some other, generally at low energy, we have different deformations, right? Generally deformations of the coordination sphere or sometimes of the ligands, but these are not actually metal ligand vibrational modes. So we have to identify them, right? So this is not what we are looking for. What about this one? No, this is like also an out of plane vibration. You see that the platinum is moving up and down the plane of the donor atoms. This looks like, right? Or not? Let me see. No, that's an angle that is changing, all right? That's again, okay. So this is the first really stretching vibration that we have, right? That's the unsymmetrical platinum chloride stretching vibration. And that comes at 321 reciprocal centimeters here. Okay. And then I guess we have the symmetrical vibration here, you see? And the two bands are separated, you see here, by 10 reciprocal centimeters. So from 321 to 330, so 10 reciprocal centimeters, all right? And then we can look for the platinum nitrogen, so that would be the asymmetrical vibration. And that would be the symmetrical one, and that is separated by 5 reciprocal centimeters. Okay, and I suppose in your trans isomer, these vibrations are degenerate for you, or not? So you have just one. Well, they are not degenerate, but the infrared intensity is 0, right? Yes. So because, yeah, I think the symmetrical vibration will not change the dipole moment of your molecule, right? So it will be infrared inactive. So we will have 4 stretching vibrations, but only 2 of them will be active in infrared. While for the cis isomer, we have the 4 of them active, right? So if you go and compare with the experimental spectrum, this is actually what you see, right? So just 2 vibrations or the 4. Actually, you have first the platinum chloride vibrations, and at higher wave numbers, the platinum nitrogen vibrations. Why is that? Yeah.
It's because of the mass of the chloride.
Correct. So the vibrational frequency depends if you take an oscillator as a model.
I don't know the translation. The time it's mass reduced mass.
Reduced mass, yes. So then it depends. Well, it's 1 over 2 pi times the square root of K, which is the force constant. So the stronger is the metal bond, the higher is the energy of the vibration, and then it's divided by the reduced mass. So if you increase the mass of your donor atoms, you shift, yes, in this direction, your vibrational frequencies, right? Okay, so that's pretty good. And let's try now to calculate molecular orbitals. So I will do it for the isomer that I have optimized, okay? And you can do it for the one that you have, of course. So let's launch the calculation. So we will use exactly the same model. We will do just an energy calculation. I'm sorry. Yeah, we are using the optimized geometry, right? So be sure that you are working with the log file generated after the optimization. So you are using the optimized geometry. So here we select just energy because our geometry is already optimized and we have characterized the structure with a frequency calculation. And then I think if you have all as it was, we need just to add, well, I didn't add title all the time, but well, never mind. I think it will work, hopefully, by adding here as additional keywords, pop equal form over here. Okay, hopefully it will work like that. That tells the program to perform a population analysis and to store in the CHK file the wave function that we need to visualize orbitals, okay? So I actually never do it like this. Hopefully it will work. So I just will add pop before the name. So I know that I have stored my orbitals there and I will submit. You know, I generally run the calculations in the supercomputer. Then I have to transform the CHK file into an ASCII file, download it, and then I visualize orbitals. So I think I never did it before in my laptop, but it should work, hopefully. Okay, calculation was extremely fast. You got it? POP, equal full, F-U-L-F. Yes. All right, so this is the critical step. So file open, and we should open the CHK file. Where is my pop? Here is this, okay? So the checkpoint file we have to open, and hopefully this will work. Yeah, so I got the structure. This is good. So that checkpoint file stores also the structure apart from the molecular orbitals and so on. And now we can go to surface. Sorry, results, surfaces. You got it? And here in surfaces, we have to generate a cube. A cube is a different type of file that contains, for instance, an orbital. We can calculate also the electron density. We can calculate different properties that are related to the wave function, of course, right? So let's select new cube. And the first thing we have here by default is HOMO. So let's calculate the HOMO. Okay. And now there is a window here you see on the bottom. Is it working? It's already done. Okay, surface atoms. I will select here, add views for new surfaces. Because if I don't click there, if I open different orbitals, it will plot different orbitals within the same window, in the same molecule, okay? So surface actions, new surface, and it should give me the HOMO. Ah! Oh, beautiful. Beautiful. So it looks like the HOMO, according to this relatively simple calculation, right, contains quite some metal D character, you see there, right? So that orbital here looks like a metal D orbital. Well, I didn't pay much attention to the orientation of the molecule, okay? But it looks like this D orbital is going in between the ligands. So it should be, yeah, DXY, DXZ, or DYZ, depending on our reference frame, right? Actually, we can also see we go to view Cartesian axis, we can add the Cartesian axis, right? So we see here our reference system, how it is, right? So this looks like DXY orbital, at least to me. Probably I think in your trans-isomer, your Z-axis will most likely be perpendicular to the plane of the molecule or not, is it? So you go to view Cartesian axis, I think. You got it?
It's a bit lagging, so.
Really? So it's not matching the C2 axis of the molecule?
No, it's just the DC.
Ah, okay.
So it's a bit.
So I think it should. Okay. Okay, it's just the graphical card or something that is. You could add the axis. Yes. Where is the Z axis? And the C is okay. So the transit of that. You have the axis. And is it perpendicular to the plane of the molecule? Okay. You did it. Did you open the CHK height or the log height? Okay. No, you need to open the checkpoint file to generate orbitals. So this is where that one. Wow, if that's the right name, yes. So now results, surfaces, new cube, and molecular orbital, you have other options there. So that's the HOMO already. Okay, very good. And you see that the Z axis is indeed perpendicular, I think, to the. So you go to view Cartesian axis. So the Z axis is perpendicular. It matches the C2 sorry. Yeah, then you need to go to results, surfaces. Well, and then cube axis, new cube, and then you generate, yes, that's the whole place. And then afterwards you go to here, surface actions, new surface. Yeah, surface actions, so you check there. And there you go. You can rotate and then so on. You have the orbitals. You need to use the CHK file from your Bob calculation. it should be the one where you selected pop equal full, otherwise you will have to store the orbitals. Surface and cube. Okay, that's the HOMO already. So okay. And then before generating so that you get a new window. One now it's ready. Surface actions, new surface. Divide. You're welcome. Okay, so let's check the LUMO now. So going to the previous window, I simply create a new cube, and now I select here LUMO. And of course, we could like generate any other molecular orbital. Okay. Now, if I select the molecular orbital 27, that's the LUMO, new surface, and there it is. And it is indeed a dx squared minus y squared orbital, you see it. And of course, this is anti-bonding with respect to the interaction with the ligand. That's an anti-bonding molecular orbital. So it looks good, right? And you could, yes, load any other molecular orbital, of course. And you can load a number of other properties related to the electron density. For instance, yeah, well, the electron density itself and yeah, different properties.
Possible to show the diagram, the molecular orbitals.
I think you can actually, but you have to load the orbitals. Let me see. I think it's what it was. Tools, molecular orbitals. And there you have the energies and of the empty and occupied molecular orbitals. And you can display even, those that you have loaded. So if you load if you create a cube file for all of them, you have even the complete list with the views of the molecular orbitals.
And also there's the diagram.
Yeah, and the diagram. Yeah.
And
Yes, but only pictures for the ones that you have load. So in my case now is HOMO and LUMO only, but I can like generate cubes for all of the orbitals, and then I will have the complete molecular orbital diagram. Okay. So yeah, and there are many other things that you can do, of course. Do you have any, I don't know, question or suggestion? So yeah, there are many other properties that you can like calculate, but then of course, the more sophisticated is the property, also the more sophisticated is the method you need, and so on, right? But yeah, you can, for instance, calculate NMR chemical shifts or things like that that may be useful, right? Okay, I didn't compare the geometries, but well, that's, oh yeah, we didn't check which one of the isomers is the thermodynamic one, right? So the active against cancer is the cis isomer, right? But which is the most stable one thermodynamically? So, okay, so we have to compare the numbers among us. So in my case that I have the cis isomer, in summary thermo, my Gibbs free energy with 0-point energy correction is 262.25. $25.0 something, 25.0295. So that's my G. Well, by default, this is calculated at 298 degrees by the program. You can also select another temperature, but you know that G is depending on temperature, of course. So this is for the cis isomer. and this is minus. So you could maybe check your value for the trans isomer. So it should be minus 262 point. It's the last value on the list, or almost the last value. You don't find it?
Yeah, but it doesn't open the thermal window.
You need to open the log file, not the CHK. If you selected frequency, it should be there. If you didn't run the frequency, then it's not. You got it?
Yeah. Thermal plus thermal free energy correction, right?
Yes.
The last one. So 2 and then after the point 275054.
Okay. So 0.27 trans, sorry. And 0.25 cis. Okay. So the active one is not the thermodynamically stable species. But you could read, that with platinum ligand exchange reactions are slow, so that you can just find a way using the trans effect to prepare one isomer or the other, right? But yeah. Okay. So you don't have questions? Do you have questions? Any suggestion? Is there anyone interested in some specific problem that we could try to calculate? Should be something small, but it's too big. Okay, if not, I think we can just stop here. And yeah, hopefully you have seen some of the, let's say, possibilities that computational chemistry is offering. And hopefully this will be helpful for you in the future, or at least that will probably allow you to understand if, some calculations may be of some help for some specific problem that you have. And you could maybe get in touch to some computational chemist that is around, or maybe even starting yourselves doing some calculations. Anything else? We'll stop here. Okay. Thank you very much for coming. It has been a pleasure.
Thank you.
Thank you. Okay, so I think I can close the meeting. Yeah.